Okay, welcome back. This is the second part of the partial fractions video, video 12 in the series. So in this particular video, we're going to be looking at case number 3, case number 4, and the special case for partial fractions. So in the other video, in the previous video, we looked at case 1 and 2, and now we're looking at case 3, whereby the denominator has non-repeated prime quadratic factor. So in other words, we have a non-factorable quadratic function. The process here is quite simple. What you'll notice is that the numerator is not simply a variable like we had in the previous videos and the previous cases. Here we have a linear equation. Why? Because the denominator is quadratic. So if we have a non-factorable quadratic function in my denominator, then I have to put a linear function in my numerator. So let's take a look at some examples. For example, we have a combination here of actually a case 1 and a case 3. This part right here would be the case 3. You can see that it's non-factorable quadratic function. And the same thing with the second example. Once again, this is quadratic and it's not factorable. So once again, it's a combination of a case 1 with a case 3. So let's go through an entire example. Let's see what happens. So I take a look at my denominator and I try to identify which cases these fall under. And we can see that the first one is a distinct linear equation. So therefore, I know that it is a case 1. I see that the x squared plus 3 is a quadratic, which is definitely non-factorable. So therefore, I break it up this way. Now remember, like we said in the past videos, some teachers prefer using a sub 1, a sub 2, a sub 3. I prefer using the letters of the alphabet A, B, C, D, and so on and so on. So because the first case is x plus 2, it's simply a. It's a number, it's a variable. And then because the second part is quadratic, I end up putting a linear equation above that, bx plus c. All right, the process doesn't change at all. We multiply through by the LCD to end up with a linear equation. Now, at this point, I need to eliminate 2 of the 3 variables. So, I chose x to be negative 2. And in doing so, I end up eliminating the bx plus c. So I replace all my x values with negative 2. I evaluate and solve for a. And a has a value of 3. Okay, so let's continue with the equation. So here we go. We have the value of a, which is 3. Now I'm going to choose x to be 0. This way I get to eliminate variable b, replace all x's with 0, solve for c, and I get c is equal to 1. Okay, so I have the value of a, I have the value of c. Now I'm going to replace it once again into my equation and choose a value of x that will allow me to solve for b. So I chose x to be 1. And then blah, 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 blah. Don't do this on any exam, but when you solve for b, you end up with a value of b equaling 4. So my partial fractions for this particular question is a over x plus 2 plus bx plus c over x squared plus 3, and the value of a is 3, the value of b is 4, and the value of c is 1. And there you go. Okay, so let's take a look at the integration, or finding the antiderivative of the previous question we just did. So we already found the partial fractions, we broke it up. Now, what we're going to do is we're going to focus on this part right here. And what we notice is that it doesn't fit any of the previous patterns that we've seen in other videos. So what do I do now? Well, it requires a little bit of algebraic knowledge. What we're going to do is we're going to simply break it up into 2 parts again. So we're going to have 4x over x squared plus 3 plus the integral of 1 over x squared plus 3. In doing so, this is what happens. This part right here is simply a logarithmic integration. This part also becomes a logarithmic integration, but there's some modification that's required. And the last part resembles something called the inverse trigonometric integration. So you can go take a look at past videos how to find logarithmic integration or logarithmic integration with modification, or even the inverse trigonometric integration. So this is the way we break up this particular question. We find the partial fractions, and then to be able to find the integral or find the antiderivative of 4x plus 1 over x squared plus 3, we break it up again in a form that we can recognize, in a form that we know. In the end, we end up with 3 ln the absolute value of x plus 2 plus 2 times the ln of the absolute value of x plus 3 plus arctan x over root 3 over root 3, and then don't forget to add your constant c. And there you go, it's done. Okay, so I'm going to throw in the special case at this point. So the special case is not necessarily one of the cases that we've seen for partial fractions. It's really a process of solving for my variables. So we're given this particular question. Now, if you looked at the last video, you will recognize that this is a case 2, and therefore I set up a case 2 in this way. So we have a over x minus 1 plus b over x minus 1 all squared plus c over x minus 1 cubed. Okay, nothing changes when it comes to the process. I'm going to multiply through by my LCD and obtain a linear equation. Fantastic. Now, looking at this, if I were to choose x to be 1, I would be able to eliminate a and b and solve for c. However, after that point, I'd kind of be stuck. So what do I do now instead? Well, I try to find a way to set up a system of equations. And how do I do this? By simply distributing everything. So x minus 1 all squared becomes x squared minus 2x plus 1. Distribute the a, I get ax squared minus 2ax plus a. B distributed to x minus 1 becomes bx minus b, and then of course my plus c. Excellent. At this point right here, all I need to do is make the coefficients of the variables the same. So in other words, ax squared will be equal to 2x squared. So the coefficient of x squared is a, the coefficient of x squared on the left is 2. The coefficient of x on the right hand side is negative 2a, and b, I would let that equal to negative 1, which is the coefficient on the left hand side. And then finally the constants a minus b plus c would equal to the coefficient on the left hand side. So this is what it looks like. A would equal 2. Negative 2a plus b would equal negative 1. And a minus b plus c would equal negative 5. Let's take a look at the next slide. Okay, so here's the equation, this is the setup, this is the relation. So we're going to take the coefficient of x squared on the right and make it equal the coefficient on the left. So ax squared will equal 2x squared. So simply put, a is equal to 2. Next, I would take negative 2a plus b and let it equal negative 1. And then last but not least, I would let a minus b plus c equal negative 5. And there you go. Solve the systems of equations. We know already what the value of a is. We can easily figure out b and c, and we broke it up into partial fractions. Okay, the fourth case and final case is when the denominator has repeated prime quadratic factors. So it's similar to case 2, however, this one is a quadratic factor versus a linear factor. Once again, remember when we say prime, we mean it is not factorable. So we are unable to factor this, but yet it still has a power. So the setup is very, very similar to what we've already done. We increase the power in the denominator, and since we have a quadratic in the denominator, my numerator becomes linear. So ax plus b, the next one is cx plus d, the next one is ex plus f, and so on and so on and so on. Okay, so no matter what case we work with, we need to be really, really careful regarding the degree of the denominator versus the degree of the numerator. So when the degree of the denominator is less than the degree of the numerator, we have to use the concept, or we have to use the process of long division to simplify, and then of course decompose or find our partial fractions. So let's assume that this was being asked of us. So we were asked to find the antiderivative of 2x cubed plus 3x squared minus x plus 16 over x squared plus 2x minus 3. Okay, we'll notice that the degree of the numerator is greater than that of the denominator, so therefore I need to use long division. So let me show you how it's done. Okay, so I'm going to show you how we perform long division. I've done this in other videos before, so just a little reminder, a little refresher. So we're going to multiply x squared plus 2x minus 3 by 2x and end up with 2x cubed plus 4x squared minus 6x. Okay, we're going to subtract. We're going to end up with negative x squared plus 5x. We're going to bring down the 16. We're going to multiply by negative 1. I end up with negative x squared minus 2x plus 3. Subtract once again, and end up with 7x plus 13. Now, 7x plus 13 is my remainder, x squared plus 2x minus 3 is my divisor, and 2x minus 1 is my quotient. Remember the way we set up our answer? 2x minus 1, which is the quotient, plus the remainder over the divisor. Alright, so the original question asks us to integrate this particular question. It's broken down into two parts, which is the integral of 2x minus 1, and then plus the integral of 7x plus 13 over x squared plus 2x minus 3. And there we go. Okay, and the way I end all my videos, of course, and I tell all my students, practice, 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 extremely important. You can find, any questions online regarding the 4 cases that we discussed. So remember that this video was broken up into 2 parts. Part 1 had case 1 and 2, and part 2 had case 3, 4, and the special case for solving.